So the last thing that we're going to do in section 10.4 is look at arc length in polar coordinates. So you've got a section of a polar curve like a loop inside a limicon, or for example one petal of a four petal rose, and you want to know how long is that, what is the length of that curve. Or you got something like the spirograph curves. You want to know what is the length of that curve. Well, the length is adding up the little pieces of arc length, ds. So think of that as an arc length element. And what is ds in in parametric coordinates? It's dx dt squared plus dy dt squared, square root, and then dt. So that's parametric. Now, what if we change theta to our parameter? Okay, and recall that dx d theta, we did these when we found the slope of a tangent. Dx d theta is dr d theta cosine theta minus r sine theta. Dy d theta is dr d theta sine theta plus r cosine theta. So that's the numerator and the denominator of the slope calculation. So then if we use theta as our parameter and work this out like it's a parametric equation, then we get the following: dx d theta squared plus dy d theta squared instead of t. Well, dx d theta right here, so put that in here. Dy d theta right here, so that goes in here. And now FOIL this out. So your first terms, you're going to get a dr d theta squared and a cosine squared. Outer terms, you get r negative r dr d theta sine cosine. And inner terms, same thing. So you get two of those, r dr d theta sine cosine. Last terms, negative times negative, positive, r squared and sine squared. And then FOIL this one out. So same thing, except a plus sign in the middle instead of a minus. So, and then we're adding those guys together. That's this plus sign. Well, this guy will cancel with this one. Okay, so what we are left with here is that first term, here, dr d theta cosine squared. This first term here, dr d theta squared sine squared. And then the same with the r squared sine squared here, plus r squared cosine squared there. Well, notice that this is a common factor in the first two terms, and r squared is a common factor in the last two. So factor out this common factor in front there. Cosine is left here, and sine squared is left here. Cosine squared plus sine squared, 1. Same thing here. Factor out your r squared in front right there. Sine squared's left here. Cosine squared's left here. Sine squared and cosine squared is 1. So you're just left with dr d theta squared plus r squared. Okay, so that's our derivative in terms of, that's our arc length element in terms of r and theta. So then what is the length of a curve in polar coordinates? Well, L is the integral from a to b, and this will be angles. Dx d theta squared plus dy d theta squared, which turns out to be square root dr d theta squared plus r squared d theta. Okay, so we'll be doing this instead. This was parametric, and this is polar. So here, let's find the length of an infinite spiral. R equals e to the negative 2 theta. Theta goes from 0 to infinity. So this is kind of a cool example. We've got this spiral curve here. And it starts when theta is 0, r is e to the 0, which is 1. So a 0 angle, we start out at 1. And then you spiral counterclockwise. And it spirals in exponentially. So it just gets tighter and tighter and tighter. So we want to know what's the length of that curve. Okay, well, our starting angle, if we let a radial segment sweep over this curve, starting angle is 0, and 2 pi, 4 pi, 6 pi. It just keeps on going as that gets smaller and smaller. So it starts at 0, and then it's going to go to infinity. Whoops, sorry about that. So L then is going to be the integral from 0 to infinity, square root, and let's see. Yeah, this one there's not really a lot of simplifying. dr d theta, so here's our r. So e to the negative 2 theta times negative 2. So this will be negative 2 e to the negative 2 theta. That's r, and it gets squared. I'm sorry, that's dr d theta. It gets squared. And then r is e to the negative 2 theta. So plus e to the negative 2 theta, and that guy gets squared. And we integrate that d theta. So, well, first thing we need to do is replace infinity with a limit. So this will be the limit. Integral 0 to b. We would let b go to infinity. And then we are integrating the square root here. Let's simplify these. So square the negative 2, you get 4. Square the e to the negative 2 theta, that's power to a power. You multiply exponents, e to the negative 4 theta. And then plus, this will be another power to a power, e to the negative 4 theta, d theta. So this is just limit b goes to infinity. And then notice these guys are like terms. That just gives us 5 e to the negative 4 theta. And then that's underneath the square root. So this would be integral from 0 to b, and then square root 5 e to the negative 4 theta d theta. So we can break this apart to root 5 and root e to the negative 4 theta. But the square root of e to the negative 4 theta is e to the negative 2 theta, because that's what you square to get this. So actually what we've got left then is the root 5 we can take outside the integral. So this would be limit b goes to infinity. Got a root 5 outside. And then integral from 0 to b. And then really what this is square root of e to the negative 4 theta is e to the negative 2 theta squared. So the square and the square root cancel each other. We are just integrating e to the negative 2 theta. And so this will be limit b goes to infinity. Antiderivative of e to the negative 2 theta here is e to the negative 2 theta. Well, I need my root 5 outside. And the antiderivative is e to the negative 2 theta. And then instead of multiply by negative 2, we're going to divide by negative 2. So this will actually be over negative 2. And we're evaluating that from 0 to b. Well, the negative 2 down here, we can factor that out in front with the root 5. So this would be limit b goes to infinity. Root 5 divided by negative 2, so that's negative root 5 over 2. And then b plug in here. So this would be e to the negative 2b minus plug 0 in for theta, e to the 0, which is just 1. So now as b goes to infinity, this will be a big negative power. So it'll be like e to the negative infinity. This guy approaches 0. That approaches 0. So 0 minus 1, negative 1 times negative root 5 over 2, positive root 5 over 2. So how cool is that? Even though this thing doesn't infinite amount of revolutions, it's only got finite length. So obviously this can't exist in the real world, but still a cool problem. All right, with that, you should be able to try WebAssign section 10.4, problem 6.